So you want to know if the data point is an outlier and you want to figure it out. So we're going to talk about two tests, Q-test and a Z-test, or Q-score and a Z-score. So Q-score is our value of Q. So we take our data point of interest, x of I, subtract off the average, and we divide it by the range. So Q-score here is whatever our data point is minus the average. Typically we take the average values here. You don't need to, you can just take the plus or minus the critical values, and we divide by the range. And this Q-score, we're going to compare it to Q-critical. So if our Q-score is less than our Q-critical, it is a valid data point. Q-score is less than, this is a valid data point. If our Q-score is greater, this is an outlier. So how do we find out our Q-critical? Well, we just look it up in tables. And this may seem to be like kind of an ad hoc thing. There is actually a proof for this that kind of goes back to, we'll talk about it as we start getting more and more depth in videos about like what these tests are telling us. But more or less it's saying that based on the difference you're seeing in the range, what's the likelihood it's actually, supposed to be in there. And typically what we're going to find, especially if we're looking at outliers, typically xi here is going to make up one of these two values, either our max and our min. It's just going to basically say, does that range make sense for normally distributed data? Now, let's say we have, this does not make any assumptions. Actually, I know I just said normally distributed data. That doesn't actually apply here. Nice thing about the Q-score is it doesn't rely on Gaussians. So this is the more general test here. We can use a Q-score to kind of figure out, like, does our data make sense? Assuming we don't have to make the assumptions here about Gaussian distributions, we just have to make the assumption that the numbers are pretty randomly distributed, but not necessarily like in a Gaussian shape. What if we know we have a Gaussian shape? Well, this is where we get to a z-score. So z-score is x minus x bar all over f. So what this does is it tells us how many standard deviations we are away from the normal, or away from the average. So if you were to look at a Gaussian, it would say, are you within 1 standard deviation, within 2 standard deviations, 3 standard deviations, and so forth. Now this is really nice because we already usually we have a pretty good intuition with these standard deviations. If we're within 1 standard deviation, there's a 66% chance that it's within that distribution, within 2, 95%, within 3, 99%. The nice thing about a z-score is that it's more confident. So what you'll find is that a z-score is a bit more rigorous in terms of tossing out data points. But the limitation here is that you have to assume that you have a Gaussian distribution. If you don't have a Gaussian distribution, this is where your Q-score is going to come in a bit more handy. But because the Q-score is going to not make the assumptions about the distribution itself being Gaussian, this ends up being, we're going to say less rigorous, but not in the mathematical sense. So to say less rigorous mathematically means that we're kind of hand-waving. That's not really what we're doing here. What we're saying is that the burden of proof is higher. So you're less likely to reject points using a Q-score than you are with a Z-score, because the Z-score is kind of narrowing itself down to a specific subset of distributions for which we know a lot more about the information. We can make a lot better estimates about the distribution. But these are your two methods here. Q-score, assuming you don't know anything about the distribution or you don't think you have normally distributed data, or Z-score if you know that you have a Gaussian distribution. Both of these are valid ways. Now, in terms of how you pick the critical values, these are typically going to be looked at in tables. You're looking at 95, 99% confident intervals, whatever you want to. Both are going to depend, this is going to depend on the number of data points as well as your confidence, whether you want 95 or 99%. This is going to depend purely on the confidence because it's going to assume that you're treating your data sets as infinite. So this is basically like a single point t-test.